Welcome to grams per mole, or molar mass. So we've already discussed how different atoms of the same element may have different masses and how to calculate an average atomic mass. For most calculations, we can assume that all of the atoms of that element have that average mass, even though in reality none of them actually will have the average mass. They all will have some discrete mass. Note that the textbook uses fewer significant figures than are generally displayed on a periodic table, so you can more easily do the calculations in your head. That is, most atomic masses are rounded to the 10th place when in AMU, where the atomic mass of an element is the average mass of a single atom of that element. The molar mass of an element is the mass of 1 mole of atoms of that element. For example, hydrogen's molar mass is 1.008 grams per mole. Note that this is not in atomic mass units anymore. And uranium's molar mass is 238.0 grams per mole. So that number that's listed on the periodic table doesn't have any units associated with it, because what it means is that number is the average mass in AMU of a single atom of that element, but it's also the mass in grams of 1 mole of that element. For compounds, we can easily calculate the molar mass of the compound by adding up the molar masses of the constituent atoms. For example, to calculate the molar mass of sodium hydroxide, we have the molar mass of sodium, which is 23.0 grams per mole, and the molar mass of oxygen, which is 16.0 grams per mole, and the molar mass of hydrogen, which is 1.0 gram per mole. When we add up 23, 16, and 1, we get 40. The molar mass of sodium hydroxide then is 40 grams per mole. And note that the molar mass supplies us with an equality. We know that 1 mole of sodium hydroxide then equals 40.0 grams of sodium hydroxide. And for any problem in which you know a chemical formula then, you can calculate and write a molar mass for that compound, element, or ion in your data section. So be sure to include the formula of the compound, like I did here with sodium hydroxide, element, or ion on both sides of the equality, so you know that you're going from moles of some compound to grams of that same compound. If the chemical formula contains more than 1 atom of any element, then it will contain subscripts. And to calculate the molar mass of a compound whose chemical formula contains a subscript, simply multiply the molar mass of the corresponding element by the subscript. For example, the molar mass of hydrogen phosphate, H3PO4, or phosphoric acid, we have 1 mole of phosphoric acid of H3PO4 contains 3 moles of hydrogen, 1 mole of phosphorus, and 4 moles of oxygen. So we have 3 times 1 gram per mole for each mole of hydrogen. That gives us 3 grams of hydrogen per mole of phosphoric acid. We have 1 mole of phosphorus, so 1 times 31 gives us 31.0 grams per mole. So we have 31 grams of phosphorus per mole of phosphoric acid. And we have 4 moles of oxygen, so 4 times 16 grams per mole gives us 64 grams of oxygen per mole of phosphoric acid. And when we add them up, 3.0 plus 31.0 plus 64.0 gives us 98.0, so the molar mass of phosphoric acid is 98.0 grams per mole. Molar mass is the most common conversion that you're going to use in chemistry. But why? Well, measuring the mass of a substance is quite easy for us to do. But measuring the moles of a substance is far harder for us to do, because we would have to actually count an extremely large number of particles. Measuring the mass is really easy. We just put that substance on a balance. Our balances are also rather accurate and precise. So we measure the mass of a substance, and then we use the molar mass to calculate the number of moles of that substance, instead of actually counting how many particles we have. So this lets us do calculations using the number of particles of that substance without actually having to count all of them. And that was grams per mole, or